Cool.
Hello, we are the Growing Prosthetic Device Group. Our agenda is we're going to go into a brief introduction of who we are, our problem statement of this project, end state vision, our team approach, expected results, and acknowledgements. So who are we? My name is Paloma Hamilton. I'm the project manager and a mechanical engineering major.
I am Michaela Reimel. I am the internal facilitator and I'm a biomedical engineer.
I'm Katie Barnes. I'm the external communicator and I am a biomedical engineer.
Jacob Sturries, I'm the lead engineer, and I'm a mechanical engineer.
I am Jesse Vo. I'm in charge of purchasing and I'm a mechanical engineer.
Our problem statement for our project is as follows. Design and develop an adaptive prosthetic device utilizing a modular system approach for a child aged 5 to 7 years. The device must securely integrate with the child's existing socket and provide adjustability to accommodate growth. It should be cost effective, safe for daily use, and capable of extending up to 7 centimeters in length. Additionally, the device must withstand forces of 100 newtons in both vertical and horizontal directions while maintaining ease of cleaning and maintenance. Our end of state vision with respect to engineering requirements are must be able to grab and hold small objects, have a total adjustable length of 7 centimeters, be at least 3 to 4 pounds in weight, have all printed parts be strong in all directions. The device does not cause pain to our wearer. Project budget must not exceed $500, and the IPA-free waterproof index of 8. The end of state vision with respect to customer requirements are create a working prototype, have it be low cost, have it be washable, cleanable. Product has adjustability. It is proportional in weight and size to our user. Has the ability to grab objects, ability to be manufactured locally, is waterproof / water resistant, must attach to the socket easily, and is comfortable for our user.
So our team approach to the solution was purely mechanical adjustable device that adapts to pre-made sockets. The adjustment happens in the forearm, as you see with the arrows, as well as in our elbow, so they both extend out. We did a lot of design iteration and brainstorming to make meaningful prototypes without wasting material. Our proposed solution will make a prosthetic device last longer, and that can grow with a child over a 3-year period of time, making the process of getting new prosthetic devices less of a hassle. Our team is on track to deliver a final prototype that is adjustable, durable, and adaptive to any socket design.
The video on this slide shows how our device can adapt as the child ages. This slide shows how our socket bar has evolved over time from a flat piece to one that contours the shape of the elbow, and also one that can accept the cable. So the cable can then attach to the harness.
Prototype 1 was originally going to have an entire socket bar assembly on the other side with the screw heads facing outward as shown. This was then changed to face the other side with prototype 2 and with an angle to better match the socket face. Prototype 3 changes the screw track to be along the bar, while the prototype also has the entire bar offset more from the center of the radius to better match the socket end. The final and most current iteration has a smaller radius to beef up other sections, along with the final material change into nylon 12.
The forearm is developed from a simple bar to a circular shape that attaches to the elbow and the tensors.
For our fourth subsystem, which is our wrist and hand, this is where the tensors were incorporated and the wrist and hand were combined. This design iteration of the wrist system where we were able to test our design in impact and weight simulations and understand where we had to change our design to meet our specifications before printing, specifically with impact testing.
We decided to make a net attachment that would grip onto the child's socket. It is made of a rubber silicone material and cut into a lattice structure. Currently, it is attached with nylon straps that buckle on the right side of the upper arm.
The harness design we decided on was the traditional figure 8 shape. which we felt would be easiest to adjust for someone who's growing. The cable that actuates the device movement attaches where that little orange circle is on the second image, and adjusts using a screw lock to give a personalized tension that can be adjusted per person.
Simulations were performed in Fusion, where 100 newtons were placed on each tensor to simulate 50 pounds of sustained weight, as if the objects were hanging off the tensors horizontally and vertically. The safety factor being shown in discolored regions. As seen, the prototypes held up pretty well. Simulations were also performed to simulate the device falling from 5 feet on both the elbow and tensors. The device held up quite well with only sub 60 megapascal stresses.
We utilized two different kinds of tests to measure a device's capabilities. One on the left, where we drop the device from incremental heights to test its durability, and the one on the right, where we hung weights off of it in various orientations to measure the tensile strength of the joints. Team expects to see our part survive 12 drops, as well as a fall from a maximum height of 4 feet and hold a weight of 30 pounds. Currently, our device exceeds these expectations, having survived approximately 30 drops with a maximum height of 5 feet and meets the weight test expectations of 30 pounds.
And we would like to acknowledge our client, Dr. Jade Myers, our guide, Dr. Alexander Louie, the RIT Maker Space for all of our printing, and Adve and Yulia for making pretty awesome animations.